my great pleasure to introduce Lenny Heath and his student Jingyi Zhang. Lenny is a co-PI on our expeditions grant and also a long-time collaborator and a very close friend of ours from our Virginia Tech days. And Lenny was really responsible for us coming to Tech in many ways and also supporting us during that time. And he has been doing some amazing work in the interface of biology and computation. So I'm going to let him describe some of the new things he's doing. Lenny, and I hope you can introduce your student as well.
Of course.
Thank you.
Let me just say, Jingyi is my computational biology expert PhD student. She does a great job in computational biology, which she is continuing to work in, but she did delve into computational epidemiology for a while, and that's what we're going to be talking about today. And she's done a really nice job with testing, and that's what we're going to talk about. I'm going to go first, and then she's going to go next. Okay, so Jingyi and I are going to present. We're going to talk today about group testing, which is a form of testing in an epidemic situation. And we're adding the contribution of looking at social contact networks. So we're going to explain how that goes, and then Jingyi is going to say what our results are. So in an epidemiological situation, you want to do testing, and the reasons are pretty clear. You want to find out early that there's an epidemic, some infection in your community. You want to do things to break the transmission chains by surveillance. You want to control the outbreak, therefore, and how you can find a good time to resume normal life. So we've all been through that, and we've all been through testing. Typical testing is one person, one test. This is limited in terms of the use of the resources that are used. And in particular, we think of PCR testing, which is a highly sensitive and accurate, but takes some time. It's especially effective at a certain period during the time that a person is infected. We want to think about whether we have enough resources in, say, a resource-limited environment to do PCR testing, and to be more efficient in terms of the use of resources, we can use group testing. So group testing is classically represented by Dorfman's two-stage process from 1943, which the idea is take multiple samples from multiple individuals, combine them into one sample, and test that sample. If that sample tests negative, then the assumption is that everyone in that sampling group is not infected. And if the test is positive, then individuals within that group need to be tested. So when you have low prevalence, you get a more efficient testing scenario. So if you look on the right, there's 27 people divided into 3 groups. So each group only requires one test. And if nobody was infected, that would be it. But since there's one person infected in the middle group, that whole group is tested, which is an additional 9 tests, which adds up to 12 tests, which is a better number than the 27 individual tests that we normally use. So this has the potential to reduce the number of tests required and make things more time efficient. Dorfman two-stage testing is also adaptable in various ways to be even more interesting in terms of doing multiple tests that are combinatorial in nature to identify who is infected. Dorfman originally invented this scheme to test for syphilis during World War II, and this kind of group testing is still used in the blood donation situation. Dorfman is not without its challenges. It takes 2 stages of testing to complete 1 round of testing. And so it's time critical. It's best during low prevalence times, so the prevalence threshold needs to be kept in mind. If you use too large a group size, then you're likely to have some false negatives, and that's not a good thing. So you want to limit the size of the maximum group. And random group assignment is something that we will talk about later as a way of doing Dorfman 2-stage testing. And random group assignment may not be optimal, as we hope to show later. Our idea in this research is to add in a social contact network and to realize that infections spread on such a network. That way we can perhaps use Dorfman as a subroutine for doing multiple rounds of testing over time, and also be aware of the contact network and do a better job of the number of tests and the reduced number of infections. So that's our idea. It's called adaptive group testing, and that's what I'll try to explain now. One part of this is to partition the contact network into subgraphs. So one thing about partitioning is the subgraphs cannot be too large, because each subgraph will be the unit for Dorfman 2-stage testing. We will hopefully show that using the subgraph can help make a more nuanced testing regime that will do a better job. We will also look at the neighbors of tested groups to determine whether there's a big risk of them being infected in the next round. So we'll do risk correlation based on what has been found to be infected in the past and what might be infected in the future. We use an adaptive strategy over time, depending on the level of infection prevalence, the infection dynamics, and how much testing resource we have available. So the big idea is to go around this circle of testing. Each round, as we will talk about later in simulation, will be a simulated day of testing. So the first thing is do group testing on some of the subgraphs. We are assuming that we have limited testing resources, so we will only test some of the subgraphs. If there is a positive result, we'll do individual testing. At the end of individual testing, we'll estimate the prevalence that will happen in the next round and use that to adjust who we're testing. So we'll go around this circle doing testing every time, aware of limited testing resources each day and a need to adjust who we test from day to day. So the first problem that we have to tackle is graph partitioning. And the idea is we're given a social contact network, as we see on the left, and we want to partition it into subgraphs where the number of nodes in each subgraph are limited by the testing capacity. We also want the number of edges in all of the subgraphs to be as large as possible. or in other words, the number of edges between subgraphs should be as small as possible. This way, we hope to minimize the amount of transmission that we miss in the subsequent rounds of testing. So the problem here is to take a social contact network, an upper bound for the size of a testing group, and maximize the number of edges that are in the partition of the original network into subgraphs. So the subsets of the node set V will be V1 through Vm. Each one has to have at most k elements. Each induces the subgraph that we will have as a potential unit to test. And the sum of all the edges in all the subgraphs is maximized. Now, to do this, we don't have a great algorithm for this. We have a greedy algorithm for this. And we use a partition score function that takes two current subgraphs, Gi and Gj, together with the parameter k, and determines whether putting them together will still be within the bound k, and how many edges will we get if we put them together. So the partition score function is basically how many edges do we get by putting them together, except we use -1 if the size of the resulting subgraph is too big. And then we go through this heuristic, this greedy heuristic. We initially set each subgraph as a singleton person, individual. At each iteration, we look at pairs of sets that we currently have in our collection, compute the partition score function, and choose a pair that is maximum, that gives the maximum partition score function. As long as that maximum is positive, we are able to merge two sets and add them back to the collection, and of course take the Si and Sj away from the collection and iterate the process. So just one step of the group testing in this regime is as follows. So we're on to the second idea, the idea of testing according to a group priority situation. Let's say we have enough testing to test 3 of the subgraphs as we have on the left. And after testing those 3, the third comes back with a positive test. Then in stage 2 testing, we test all 6 individuals in that subgraph, and we find 2 individuals are positive. That has a result, as you see in the middle column, of 2 red individuals that tested positive and everyone else was assumed negative. Now, if you go over to the complete graph, the complete social network on the right, we've got these 2 positive individuals. This subgraph is adjacent to 2 other subgraphs, which are kind of this hashed red indication on the nodes. And those 2 will be given the highest priority for the next round of testing. We already know the testing for the ones that are in the 3 subgraphs that are indicated with green and red, but we'll give priority in the next round to the 2 subgraphs that are adjacent to positive tests. The problem that we're solving in terms of coming up with priority for the next round of testing is we have a testing capacity B, that is a total testing capacity. We have some number of tests carried out at time t, and we have a number of infected individuals at time t in subgraph I, that is x sub it. So this is we might say a random variable that is for subgraph I and time t. It is the number of infections that we know about, let's say. For the groups that were tested, we want to keep the number of tests, which is QIT, the total number of tests bounded by B. And we can say that QIT is 1 if we had a negative result, and 1 plus the size of the subgraph if we had a positive result. And we want to find as many infections as possible. So we want to maximize this sum under the constraint that the sum of the QITs is at most B. Now, we're going to have some strategy modes. We're going to have a low prevalence tracing mode that is basically what I've described so far. That is, we give testing priority to neighbors of infected individuals. If we have found that we're in a high prevalence time, we try to spread out the testing by a breadth-first testing method to prioritize as much of the population as is possible. The way we decide whether we're in tracing mode or screening mode is by looking at what's called the point prevalence, which is rho of t at time t, the ratio of infected individuals by the number of individuals tested, which is this sum. So rho of t is this sum. If the sum is high, then that means we are doing a good job of finding the infected individuals with tracing mode. Otherwise, we switch to screening mode. And this is, again, our group testing strategy. We adjust the testing order depending on which strategy we're using. Our basis for doing simulations to test our method is to use an SEIR model and to use some parameters for COVID that we found from a paper of the amount of time there is between initial infection, the first time there's a positive PCR test, the time of recovery. The recovery period is given by a normal distribution, which we'll talk about in a minute, and the probability of passing the infection along to another individual who is adjacent is given by an exponential distribution. So we have a simulation for testing our ideas, the AGT scenario in particular, but also other scenarios for comparison purposes. We initially assume all individuals are susceptible, and then we use a parameter N0 to randomly select N0 individuals for initial infection. We have two setups, real networks and synthetic networks, which we will describe later. The real networks, we give them 75 time steps, where one step is a day, and we give a testing capacity that is 15% of the population. And generally, we assume that the group size is 10. For the synthetic networks, we do it for 150 time steps, and we'll see why we can do it for a longer time later. And we have testing capacity, again, of 15%, because we're going to have 1,000 individuals in a synthetic network. Some of the key parameters to this simulation are the initial outbreak size, which we chose as 5, The parameter for whether someone will infect someone else is exponentially distributed with a parameter lambda. Incubation period is a parameter alpha, which we chose 7. And the recovery is given by a normal distribution with parameters 7 and 4. Onto the data sets. There are synthetic data sets, which we use some standard models. Barabasi-Albert, Chung-Lu, Erdős-Renyi, stochastic block model, and Watts-Strogatz. We also have another model, Waxman's, which I'll describe in a minute. We see that all of the number of nodes for all of the networks is 1,000. The degree is chosen to be approximately 6, expected to be 6. And the diameters vary among these models. You'll see that there is the Barabasi-Albert model has a small diameter of 5. The Waxman model has the largest diameter of 11. Waxman's model was chosen, and it's not a normal model in most people's kit bag. It's a model that takes into account the geometry of the plane. So the idea is that a random selection of individuals is placed on the plane, let's say n of them, and then each pair has a Euclidean distance between them. And the probability of there being an edge between two individuals is chosen according to this equation. The further apart they are, that is, the larger the Euclidean distance, the lower the probability. There are two parameters, alpha and beta, that control also this probability, and L is the maximum distance between any two pairs. So the Waxman model is there to simulate that close by people are more likely to be connected in a social contact network. And we were just trying this model out to see how it would perform. We also had some real contact networks from a place socio patterns. These are networks that are gotten by things like nearness by, say, cell phone or some other technological method of determining whether two people interact over a period of time. And so these networks tend to be more dense, have a higher degree than what we chose for our simulated networks, and they have lower diameter. Again, we chose these to see what kind of results we would get with real contact networks, but as you can see, they're small, the largest one being 403 individuals. Okay, on to evaluation. This is where Jingyi takes over. Jingyi?
All right, cool. So for evaluation, we compare our testing strategy in terms of the maximum outbreak size, the maximum number of secondary transmissions, the total number of tests, and the number of uninfected individuals by the end of simulation period. For the first 3 metrics, the lower the values, the better the strategy performs. For the last one, the higher the better. We report the average of results over 100 simulations for each experiment. And there are 3 baseline strategies. Baseline strategy number 1 is the individual testing, denoted as IT. It randomly draws B individuals from the population without exceeding the testing capacity and tests individually. Baseline strategy number 2 is the random group testing. It applies randomly selected groups as described in the original Dorfman's method. The group size is K, and the number of testing performed at each time step is bounded by the testing capacity. Baseline strategy number 3 is graph partition-based group testing with the random testing order, denoted as GRGT. This is a simplified version of our testing strategy. It only focuses on the underlying information collected from the social contact network. This strategy first divides the social contact network into M groups, then randomly select groups to perform the two-stage testing. We simulate AJT on 6 synthetic contact networks and 7 real networks and compare it with 3 baseline strategies. Also, we explore the testing performance of AJT at different population scales, group sizes, and testing capacity. Now let's dive into some details. The first experiment tries to examine the performance of the testing strategies on synthetic contact network with population of 1,000. Here we want to highlight how our method is in containing the outbreak and reducing the secondary transmission. Here we have 2 key performance indicators plotted on the y-axis. So on the left, we have the maximum outbreak size, and on the right, the maximum number of secondary transmissions. So for both metrics, the lower the values, the better the strategy performs in controlling the spread of the infection. So as we can see from the charts, our strategy representing the blue bars yields the best performance across all synthetic network models. Here we have all infected percentage charted against different network models. The higher the values, the better the strategy performs in saving susceptible individuals from infection. Still, our methods colored in blue shows the best performance here. Since the network structure is heterogeneous, our AGT can save about 87 to 90% of the tests compared to the individual testing methods. And AGT successfully reduces the maximum outbreak size by about 3.9 to 46% as compared to other strategies, which helps reduce the burden on the public healthcare system during outbreaks. Moreover, with the help of the tracing mode in AGT, the number of secondary transmission is lowered by approximately 1.9 to 27%. Now, let's focus on the Chono model. So results for the remaining network generation models follow a similar pattern, so they're omitted here. Our objective is to explore the daily changes in the number of both infected and uninfected individuals and highlight how each strategy manages the outbreak peaks and protect susceptible individuals from infections. So this plot shows the daily change of the simulated infections. We simulate 100 times, and the line in the middle is the average, while the shaded area is the confidence interval. Our methods still colored in blue. We can see that AGT successfully both lowers and postpones the outbreak peak with no significant spikes throughout the simulation. And due to the timely detection of infected individuals, no large regional outbreaks result from secondary transmission. In contrast, if we look at the GRGT colored in red, displays strong instability. There are multiple repeated rallies in the early period of outbreak, and it only gradually declines after reaching the peak of the outbreak. Individual testing, colored in green, and RGT colored in orange, performed roughly similar, but random group testing is more volatile and declines more slowly after reaching the outbreak peak. Thus, here in the uninfected daily change plot, we can see that random group testing leads to fewer uninfected individuals than individual testing, while our methods colored in blue protects a greater number of susceptible individuals. We also conducted experiments to compare the performance AGT with baseline strategies under varying transmission settings. Recall that we described the infectious disease transmission process using an enhanced SER model with heterogeneous infectious probabilities to incorporate the characteristics of SARS-CoV-2 infection. In particular, each individual has a random infectious probability drawn from a predefined exponential distribution. The expected infectious probability is given by 1 over lambda. So taking Chodo model as an example, this experiment aims to assess AGT's adaptability and efficiency in diverse transmission scenarios compared to other strategies. So here we show 4 plots. On the upper left is the uninfected percentage, the higher the better, all the others is the lower the better. So AT consistently outperformed the baseline by achieving a higher percentage of uninfected individuals and requiring a lower total number of tests. This highlights the effectiveness of our methods in containing the disease transmission while optimizing testing resources. The advantages of AGT became even more significant as the disease transmission capability increases, providing protection to a greater number of people. Although individual testing colored in green achieved a slightly lower outbreak size at very high transmission settings at the lambda around 4, if you can see my point here, but it consumes 576% more resources compared to our methods. Moreover, our methods exhibited stable performance in controlling secondary transmissions, ensuring that effective containment of the spread of the disease. Moving on to the next, we simulate various testing capacities ranging from 5 to 25% of the whole population to investigate how testing capacity affects strategy performance. Here we want to highlight number 1 is the impact of minimal testing capacity on disease containment. Number 2 is effects of larger testing capacities on strategy outcomes. And we want to understand the critical threshold for testing capacity in ensuring effective disease containment across various network models. So here are the results of AGT on 6 synthetic networks at different testing capacities. We have 2 key performance indicators plot on the y-axis. On the left, we have the maximum outbreak size, and on the right, we have the maximum number of secondary transmissions. So in general, the greater the testing capacity, the smaller the outbreak size, and the fewer the number of secondary transmissions. And also the greater the number of susceptible individuals that will be protected from infection. The spread of the disease is not effectively contained on any network model when the testing capacity is 5% of the whole population, since the limited testing resources, they're insufficient. Especially the Barabas-Albert model, the outbreak size reaches 15% of the whole population. But when the testing capacity rises to 10%, it only performs well on the smaller model, but still does not effectively protect susceptible individuals on the other network models. There are no significant differences on each evaluation measurement after the testing capacity reached more than 20%. Approximately 95 to 97% of susceptible individuals are protected from infection. Additionally, we compared the performance of AGT with 5 different group sizes ranging from 5 to 25. As shown in the plots, when the group size increases, the strategy's performance does not keep moving. The optimal group size varies slightly across network models instead. When the group size is 20, colored in blue, AGT performs better on some network generation models such as the Chono model, ER model, and SVM, which allow maximum protection of the susceptible population, but required fewer tests. The small world and the maximum network models, a group size of 15, colored in red, results in the lowest number of infections and the smallest outbreak size. We also investigate how the population scale affects the performance of the testing strategy. We simulate 4 population scales ranging from 500 to 2,000 and set the initial outbreak size as 1% of each population and testing capacity as 15% of the corresponding population. All the other parameters remain unchanged. Here we have the first row as uninfected percentages. The higher the better, and the last 3 rows are total number of tests, maximum outbreak sizes, and maximum secondary transmissions. The lower the better, and each column here corresponds to population from 500 to 2,000. As can be seen in these figures, the performance of individual testing colored in green gradually becomes more deficient as the total population climbs, while the performance of group testing strategies gradually improves. Our proposed strategy consistently protects the most susceptible individuals from infection when the population scale increases, regardless of the network structure. Moreover, our method is always optimal in terms of saving testing resources and reducing secondary transmission throughout all simulations. It saves 87% to 90% of the testing resources compared to individual testing and achieves a 9% to 20% reduction compared to random group testing. Continuing our journey, since we noticed that the total population of each real data set is limited, but the average degree is relatively high, the spread of disease may be greater than the ones that we simulated on this synthetic network. So here we further develop a variation, noted as AGT variation, of our proposed strategy, which gives higher priority to the tracing mode when the estimated prevalence is high. Here we show the performance of testing strategies on 7 real contact networks, and the y-axis of the plot is the uninfected percentage. The higher, the better. So generally, the group testing strategy means the strategy 2, 3, 4, and its variation performs better than the individual testing colored in green. And our proposed methods successfully saving more susceptible individuals from infection. The next slides, we have total number of tests, maximum outbreak sizes, and maximum secondary transmission. So they are all the lower the better. As we can see that group testing strategies can save 76 to 88% of the testing resources, but the difference among different group size testing strategy is insignificant. It is worth noting that our original strategy is not effective in reducing the outbreak size on high-density real networks, but the variant for high-density networks significantly reduced the outbreak size on the SFHH, the hospital network, but does not differ much from the random method on the other dataset. As we evaluate AGT's effectiveness, our study paints a clear picture that group testing significantly outperforms individual testing in efficiency. And with adaptive strategies, we can do better. We observe that even with a modest testing capacity, saying 15% of the total population, it can produce acceptable results with adaptive group testing. This is encouraging, especially in resource-limited settings. And looking beyond COVID-19, our group testing strategy also has the potential to be applied to other infectious diseases such as HIV and maybe influenza, as the underlying principle of early identification of infected individuals and reduction of the burden on the public health system remains consistent across different diseases with similar transmission patterns. The adaptability of this strategy across different pathogens could be transformative. Network size also plays an important role. Our simulations on the synthetic models have provided deep insights, highlighting that adaptive group testing's effectiveness can scale with the network size, which is crucial for real-world applications. Optimizing AGT presents a complex puzzle, so the optimal group size is limited by practical constraints such as diluent effects and testing sensitivity, particularly in low prevalence scenarios. In considering the application of AGT within dense real-world networks, we encounter a non-scenario. The inherent advantage of AGT is somewhat lessened when compared to random group testing. It is crucial to recognize that the real contact networks we studied were constructed using sensor data, which may present an unrealistically dense web of interactions. The high density can accelerate transmission, presenting a challenge to the efficacy of AGT. So to enhance AGT's performance in these settings, we need a understanding of the network's intricacies is essential. Our assumptions, including perfect testing and a specific disease transmission model, are theoretical. In reality, we face the challenge of imperfect tests and variable quarantine adherence, not to mention the complexity of SARS-CoV-2 transmission dynamics and external infection reintroduction. But despite all these limitations, our findings still offer a substantive blueprint for adaptive group testing strategies in infectious disease control. As we look to the future, enhancing AGT will involve nuanced considerations like contact duration and titer sampling and vital in high-density real-world networks. And AGT shows promising potential for application to other infectious diseases like HIV and influenza something. Yet it calls for adjustments based on disease specifics. Each pathogen's unique characteristics will shape AGT's application. Moreover, real-world implementation brings its challenge, like costs, logistic complexities, and the need for broad collaboration stands between theory and practice. But with technology innovation and strategic planning and robust public outreach, these barriers are not insurmountable. All right, and last, we want to thank the support from the NSF GPCE project, and we would like to express our sincere gratitude to Dr. Patrick Butter, Yun Jen, Xiao, and Dr. Anil Valankanti for providing valuable feedback and suggestions. Thank you very much.
Thank you.
Hello, that was a very illuminating talk. Thank you. I had a question about the second stage where you do individual testing on the positive testing pools. Have you got any ideas about who should you prioritize to test first among those individuals?
The original method was test everyone
Mhm.
in a positive test group. Now, I think you're asking, can you be more nuanced than that?
That's right.
Ah, that's an excellent question. If you know something about the network, as we assume we do, I would think you could be a little more strategic about who you test in the second stage. If someone has been exposed to someone that you know was infectious in a previous round, yeah, I think you probably could. We didn't even consider that possibility, but that's an excellent idea.
Thank you.
Maybe I'll ask one. Lenny, did you get any theoretical results as well, or mostly the simulation?
It's really all empirical. We didn't know how to get any theoretical results, but that would have been nice.
Yeah, no, I know it's hard. That's why
it's hard because there's so many moving pieces in this group testing strategy. I'm certainly open to suggestions on how to pursue some theoretical ideas.
Okay. My one other suggestion was we do have now, as you know, some smaller networks in hundreds of thousands of nodes, which are synthetic, but maybe between the two class of networks, you had real versus, I would say, very stylized. There are synthetic population-based networks that you might want to consider if you like.
That would be very helpful. I will talk with Jingyi and see how many cycles she has in the day to do some more testing.
Yeah.
So I was thinking for the first step, when you use the graph partition, there are some methods available to identify, so let's say, community detection type problems, right? So do you think those methods would be useful in the first step of graph partition?
That's a possibility. The challenge we had is that the subgraph size has to be limited. And ideally, the subgraph size would be they would all be roughly the same size. So the problem has additional constraints that are not normally found with community detection. So we did not find an ideal solution in the literature that took those constraints into consideration. But if you have something that's a little more along the lines of what we need, we'd be happy to hear about it.
Thank you.
That discussion just reminds me of Stephen's method where they used Moore-Shannon reliability, and I worked on it, and we had a maximum subgraph size as a parameter. So we could go fine-grain and find communities which are smaller, and then we can adjust the parameter to have sort of a hierarchical community detection. So Maybe that could be a community detection method, which has that constraint that you're looking for.
Do you have a reference for that? I really appreciate any references that you have, because I could imagine using a better method for that step.
Yeah.
So
Yeah.
one method that I can think of is we are trying to partition this into a stochastic block model where within group connection probabilities are much higher than the intragroups. Is that correct?
Right.
And one thing I want to mention is that we are trying to do a near balanced partition, saying that we don't want some groups to be too small. We want the size are roughly the same, so that every time we can do a two-stage testing. That's why when we're looking for a community detection methods, a lot of them are like suitable for this problem. And we're really open to suggestions if there are new community detection algorithms that focus on near balanced partition of the community.
So, given the size of your networks, it would seem you could at least write an integer program to get a reasonable start. No, I mean, Lenny, of course, would know it. So I'm just questioning. Bigger networks, you'll have to use some heuristic, but many of your networks are very small. Even the synthetic networks were only 1,000 nodes, if I recall. So one could certainly write a program to try and get a reasonably good partition, because you can write as a program to do that. And that might at least tell you how much partition helps. I mean, there are other reasons, at least you can factor out the role of partitions in the outcomes.
So there are also some results for, let's say, Erdős-Zhang type graphs, where you know that if your connection probability is within certain regime, then you have very small clusters and one giant cluster. So you already have a partition in Erdős-Zhang type graph, and then you further need a graph partition only for this bigger cluster, right? And then you need this balanced partition. Okay.
Yeah. So again, anyone who has references that we could use, send it our way. And thank you, Madhav, for your suggestion of ILP. I will talk that over with Jingyi.
Okay. Yeah.
All right. Thanks again, everyone. Have a great day.
Thank you. Thank you again for the good talk. Bye.
Thank you.